Okay, I want to do some more practice on finding some areas under the curve here. So let's go ahead and do that. Let's find the value of k. Find k so that the probability that z is greater than k is equal to 0.3015. Find k so that the probability that z is greater than k is 0.3015. Why don't you go ahead and give this one a shot? Pause the video. This is something we should be able to answer on our own, potentially. See if you can do it. Assuming you've paused the video and given this attempt, I'll go through this relatively quickly here. So I need probability that z is greater than k is 0.3015. So the way I would tackle this is, if this is my normal distribution, let's try to, I want to make the peak right at there. Greater than k at 0.3015. So if this is k, then this area here is 0.3015. 0.3015. If that area is 0.3015, then this area here has to be 1 minus that. 1 minus that. So all of this area here, 1 minus 0.3015, that area is what? That area is 0.6985. So how can we try to figure this out? This is equivalent to looking for the probability that z is less than k to equal 0.6985. 6985. So I want to look for this value in our table. 0.6985. Let's go ahead and go to the table here. 0.6985. Where are we at now? Let's clear out some of these old markings if we can here. 0.6985 looks like we're right about 6985, right there. Boom. 0.52. So you should have gotten 0.52. And it's always good to reference our work, right? This is in table A3, just so we know. If someone else is looking at our work, how do we get that? We looked at table A3. Let's try another one. Example, part B. Okay, so let's go ahead and find k again. Find k so that the probability that k is less than z is less than negative 0.18 equals 0.4197. Let's see if we can't answer this. All right. K is between, z between k and negative 0.018. Excuse me. There we go. This looks good. So where are we going to be? So we're looking at negatives, right? So this is negative 0.18, somewhere right there, pretty close. And then k has got to be somewhere to the left of that. So k is somewhere over here, roughly speaking, right? And so we want the value of k that's going to give us an area. We want the k value that gives us this area to equal 0.4197. We want that area to equal 0.4197. All right. Well, if we look at the probability that z is less than negative 0.18, that's going to give us too much area. The probability that z is less than negative 0.18 is going to give us all of this area, but we can work with that. What we need to do then is we're going to need to subtract the area we don't want. So we want to take away the probability that z is less than k, which would be the area to the left here. And we want this to equal 0.4197. That should equal 0.4197, okay? And so let's see, we can look this up in the table. Let's go ahead and do that. Negative 0.18. Negative 0.18, so that's going to be on the first page because it's negative. So where is our negative 0.18 going to be here? On the first page here. So negative 0.180. Right there. 0.0359. No, that's not right. That's not right. This is negative 1.8. Yikes. This is negative 1.8. We want, be careful, we want negative 0.18. Negative 0.1 is here, and then 0.18 then, so 0, 1, 2, 3, 4, 5, 6, 7, 8. Should be 0.4286. 0.4286 there. Careful on that one. 0.4286 is what we want. So this is equal to 0.4286 minus the probability that z is less than k. That's what we're looking for. This needs to equal 0.4197. So what we're going to go ahead and do then is I'm going to subtract the 0.4197 from the 0.4286. When we do that, I've got 0.0089. And I'm going to add the probability that z is less than k over to the other side. Probability that z is less than k. So what we have now is a nice relationship. We're looking for the k value, where the probability of the standard normal random variable is less than that k value gives us a table result of 0.0089. So now we just go ahead and go to the table and say, well, where's 0.0089? 0.0089. It's going to be pretty early on here. 0.008. Start looking at your table. Here's 0.0080. 0.0089 is right there. 0.0089 is right there. Okay. Notice that that is negative 2.37. Exactly. Negative 2.37. So via table A3, we find k to be negative 2.37. Negative 2.37. So that means right here. That means this value is negative 2.37 for k. All right, that looks good. I just want to mention how convenient that was that it worked out exactly. Sometimes that's not always the case. What if it didn't end up being negative or 0.0089, but what if it was 0.0088? Well, 0.0088 doesn't show up exactly in the table, but it is right between this value and this value. Right between that value and that value. So what could you do? Well, kind of take an average. If it's right in the middle there, you basically say it's halfway between here and here. So you could do something like negative 2.375 if you wanted to, right? Or honestly, you pick either one of these. That's very close, right? But if it's not exact, sometimes you got to do like a little bit of an average in between. Okay, especially if it's smack dab in the middle of those, that's really nice because then you can just do a 0.5 or a 0.75 type thing, right? So, just something to kind of prep ourselves. A situation potentially you could come across in the future, right? Okay, there we go. So a little bit more practice on working with the standard normal table. All right, so now what I want to try to get us to think about then is we've used this table and we can answer all these probability questions about something that follows a normal distribution, but this is only for the standard normal distribution. This is only for normal distributions that have a mean of 0 and a standard deviation of 1, right? So what happens if you have a normal distribution question where the mean is not 0, right? What if the mean is not 0? Well, then you ideally would want to go to the appropriate table, right? Ideally, we'd have tables for a variety of pairs, of mu and sigma for the normal distribution, right? And if, say, something had a mean of 1 and a standard deviation of a half or something, then you could go look in that table, right? For the normal distribution. But there's a practical problem here, right? it's obviously impossible to do this for every value of mu and sigma, right? It is impossible to do this for all pairs of mu and sigma, because mu and sigma are real numbers, right? The mean could be anything, and the standard deviation could be anything. There's an infinite number of pairs. It is impossible to do this for all values. It is impossible to do this for all values, okay? So I guess the question then is, how do you tackle this in general? How do we tackle this in general? If we want, let's say x follows a normal distribution with mean, mu, and sigma squared. This little tilde symbol is just saying x follows a normal distribution. So x is a normal random variable with mean, mu, and sigma squared. If you want the probability, then we want the probability that x takes on values. Let's say, between x1 and little x2, right? How does one do that, right? Well, the way we do this is we integrate from x1 to x2 our PDF f of x dx. This is a continuous random variable, so we integrate from x1 to x2 f of x dx. All right. So what is this integral going to look like? Well, in terms of the general normal distribution with a mean mu and a variance of sigma squared, or a standard deviation of sigma, let's go ahead and write that out. x1 to x2. What is f of x dx, right? What is the normal distribution PDF? That is 1 over sigma times the square root of 2 pi e to the negative 1/2 times the quantity x minus mu over sigma squared dx. That is the integral that we have to do, right? That is our PDF f of x for the normal distribution that has mean, mu, and standard deviation sigma. So how do we tackle this integral? Well, let's take a look at this. The challenge points of this integration, it's pretty complicated, I say at the very least, because of what you have going on up here, right? The x minus mu sigma squared. If this was just e to the negative x, for example, if this was like something like e to the negative x, it wouldn't maybe be quite that difficult to integrate. So as an effort to try to combat this integral, I'm going to go ahead and set up a substitution. We're going to set up a u substitution. And let's go ahead and do that. So let's go ahead and let u, well, I don't want to use the letter u here. Do I want to use the letter u? Sure. Let's use the letter u. I'm going to say u is equal to x minus mu over sigma. X minus mu over sigma. Remember that mu and sigma are just numbers, right? Mu is just the mean and sigma is just a standard deviation. Those are real numbers. Okay. So we're going to be able to substitute that in. So that's going to go up there. So we can substitute in u there. We're going to need a substitute for dx. So let's figure out what dx is. What's the differential? Du then, the derivative of the right-hand side here with respect to x, via the constant multiple rule here, this should just be 1 over sigma dx, right? Because the derivative of a constant value, mu, is 0. So that's 1 over sigma dx. So if we want to solve this for dx, that would be sigma du equals dx. All right, so far, so good. So let's think about substituting some of these things into our integral here. Let's think about substituting some of these things into our integral. So far I've got the integral. I have 1 over sigma square root of 2 pi e to the negative 1/2. And then instead of x minus mu over sigma squared, I have the letter u now, right? We've made that substitution. That is u. So e to the negative 1/2 u squared. Dx is sigma du. Dx is sigma du. What else are we missing here? Oh, you got to be careful. We should deal with the bounds x1 and x2 as well, and maybe get those in terms of u. So let's think about that. When this is our substitution, right? So when x is equal to x1, u is equal to what? U is equal to x1 minus mu over sigma, right? U is equal to x1 minus mu over sigma. So I'm just going to go ahead and call this u1, and remember that I can punch that in the end. So I'm going to put a u1 down here, where u1 is x1 minus mu over sigma. And then when x is equal to x2, what is our u value going to be? Well, it's just going to be x2 minus mu over sigma. So I'm going to call that u2. u2. That is the variable bound, not the band, u2. Sorry, Bono. Is Bono the singer for u2? I don't know. I hope not. Or I hope he is. If he isn't, just made a glaring pop culture mistake on a recorded video that will probably never get deleted, so yikes. Let's roll with it. How are we doing here? So far, so good. So let's take a look at this. Can we simplify this integral at all? Well, this is 1 over sigma times root 2 pi, and you have a times sigma du in the numerator, so this sigma and this sigma cancel out. Okay. So what do we have here is I have a constant multiple of 1 over root 2 pi, which we can factor out of the integral in front. Integrating from u1 to u2, e to the negative 1/2 u squared du. 1 over root 2 pi, integrate from u1, u2, e to the minus 1/2 u squared du. Actually, I don't need to factor this 1 over root 2 pi out, do I? I'm going to prefer to not do that. I apologize for those of you who are writing notes on paper and pencil, where it's not as easy to erase. Maybe just hold on for a second before you change your notes, because the reason why I just want to leave this in there is because I want us to see this connection between what the heck is going on right here. What is that function right there? 1 over root 2 pi e to the minus 1/2 u squared. 1 over root 2 pi e to the minus 1/2 u squared. That function right there, is that not this right here? But instead of the letter u, I have the letter x. That is the PDF of a standard normal random variable. This is the PDF of a standard normal random variable. This is equal to, this is an integral from bounds u1 to u2 of a normal random variable. A normal random variable. I can say u here, I guess, for now. A normal random variable. But what are the parameters of that normal random variable? It has mean 0 and standard deviation 1. This is just a standard normal PDF now. This is just a standard normal PDF. So how does one figure this out? We're going to go ahead and look in the table. We're going between u1 and u2. This is the probability that a standard normal random variable is between the bounds u1 and u2. Between the bounds u1 and u2. And what is u1 and u2? u1 and u2, right, is, here's u1, that is x1 minus mu over sigma. And then u2 is x2 minus mu over sigma. x2 is, u2 is x2 minus mu over sigma. So, all of this string of inequalities, this whole string of inequalities from this stage here, we want the probability that x is between x1 and x2. That is equal to the probability that the standard normal random variable is between these bounds. Let me go ahead and rewrite that next to each other. The probability that x is between x1 and x2 is equal to the probability that the standard normal random variable is between x1 minus mu over sigma and x2 minus mu over sigma. In other words, We only need one table because every normal distribution question can be converted to a standard normal distribution question with just some different bounds. We've reduced the number of tables required to 1. Right? Every normal distribution question can be answered using the standard normal distribution. So we only need one table. We only need the one table. We only need the standard normal distribution table. This is awesome. This is really cool stuff. So the great thing about this then is if we set up our question like this, all we got to do is make this conversion here, and we make this conversion here, and then we go look those up in the table. We don't need to go through this whole integration process anymore at all. We don't need to do any fancy substitutions. We just change our bounds as we look it up in the standard normal table. Okay? So upcoming, obviously, then, is some examples of normal distribution questions that have a variety of means and standard deviations, and we'll practice converting them to standard normal distribution problems. We will leave those examples for the following video. We will see you over there.